Our goal for this lesson is to understand and solve problems that involve dependent events. So let's think about this. Jackie plays on a volleyball team called the Giants. The Giants are in a round-robin tournament with 5 other teams. That means a round-robin means that you're going to play each of the other teams once throughout the tournament. The teams they will play against will be selected at random. Determine the probability that their first game will be against the Clippers and their second game against the Maroons. So we know we've got the Giants, the Clippers, the Maroons, and then there are 3 other teams. We don't know them. We'll call them X, Y, Z. Now, because she is a member of the Giants, they're not going to play themselves, so we don't even consider them. But if we want to consider the probability that the first game will be against the Clippers, well, how many teams are called the Clippers? We're assuming only 1. How many teams are there that they could play against? There are 5. So the probability that they're going to play the Clippers in their first game is 1 out of 5. And that their second game will be against the Maroons. Now the Clippers are out of the mix. We've already played them. Round robin means they're only going to play the Clippers once. So now, how many teams are called the Maroons? We're assuming just 1. How many teams are left? There are only 4 teams left. So now, because we wanted both of these to occur, it said first against the Clippers and second against the Maroons. We are going to multiply these probabilities together, and we have a 1 out of 20 chance that this will occur. Let's reflect on this. How did the probability of the first event affect the probability of the second? Well, because in the first event we had 5 teams to choose from, but then we played the Clippers and we can't play the Clippers again, now there are only 4 teams left. So that second probability depends upon what happens in the first probability. So dependent events are events whose outcomes are affected by each other. For example, if 2 cards are drawn from a deck without replacement, so you're drawing the card and you're not putting the card back into the deck, then the outcome of the second event depends on the outcome of the first event, which was the first card drawn. Because that first card isn't put back, so we can't consider it again. We now have less cards to choose from, and that first card is no longer an option. So we want to consider the following example. From a standard deck of cards, 2 cards are drawn at random without replacing the first card. Now it is very important you read these questions carefully, because some might be with replacement and some will be without. And it's very different in how you solve the answer. So here we're not going to replace the first card. So we want to determine the probability that the first card is red and the second card is black. Well, what we have to know is that there are 52 cards in a standard deck. There are 26 that are red and there are 26 that are black. So we do need to know that information. So let's start with our first card. First card is red. What's the probability of that occurring? 26 out of 52. 26 red out of 52 cards. Now remember, we're pulling out a card. We're not putting it back in the deck. So now, how many cards are left to choose from for the second draw? There's only 51 left. Now, was the black dependent upon the red? Can a black be a red card? And the answer is no. So you've pulled out a red card, all 26 black cards are still there. So we can still choose from any of the 26. Multiply these together, 676 out of 2,652. If that doesn't really make a whole lot of sense to you, you can write it as a decimal, 0.2549. Or you can write it as a percent, so about 25% chance of this occurring. Now, what's the probability that they are both diamonds? Well, we have to understand there are 13 diamonds in a deck. So On our first draw, we can choose any of those 13 diamonds. And there's 52 cards for us to choose from. But now in our second draw, remember we've chosen a card. We've pulled out a diamond. How many cards are left in the deck? There's only 51 left to choose from. Our first pull, we pulled one of those diamonds. We want the next one to be diamond, but one of them is out. So how many are left? There's only 12 diamonds left. So we have 156 out of 2,652 options. Again, if that doesn't make sense to you, write it in decimal form, or you can write it in percentage. So there's only about a 6% chance that you are going to pull both cards being diamonds. Now we want to look at the first card is a 10 and the second card is an ace. There are 4 10s in a deck. There are 4 aces in a deck. So let's make our first draw. We have 4 10s to choose from out of 52 cards. We pull a 10. There are only 51 cards left for us to choose from. We now want to pull an ace. We pulled a 10 the first time, so there are still 4 aces left in the deck. So our probability is 16 out of 2,652, or 0.00603, or just under 1%. So the probability that you're going to pull a 10 and then an ace is really less than 1% probability. Not very likely. All right, let's consider this one. Parker has 8 identical black socks and 10 identical white socks loose in his drawer. He pulls out 2 socks at random. Determine the probability that he pulls out a pair of mismatched socks. That is, one black and the other is white. So how could we do this? If they're going to be mismatched, he might grab a black and then a white, or he might grab a white and then a black. So those are the 2 ways that we could pull out mismatched set. So we have to consider these. So the black and the white. So first of all, we have 8 black socks. There is a total of 18 socks in the drawer. Now, once he pulls out that black sock, there are only 17 socks left to choose from. There are still all 10 white ones in the deck. Now, if we look at this other option, if he first pulls out a white, there are 10 white and we had 18 socks to choose from. We pulled out a white, there's only 17 socks left, and there are 8 black ones. So we consider these probabilities, so 80 out of 306, 80 out of 306. Because both of these could occur, we add our probabilities together. So you get 160 out of 306, or you could write it as 0.5228, or a 52% chance of this occurring. So the key with dependent events is that if you are not replacing the first item that you pick, or if you are in a tournament play and you can't play the same team again, when you now look at the second probability, you are dealing with a smaller sample space. There's not as many elements to choose from, so you need to take that into consideration.